Hello everyone, welcome to this video. In this video, I pose to you this question that can factor groups which are created by the center. So that means we are taking the subgroup as the center of the group itself. So the group, and if we are taking the center group as its subgroup, so the whatever is the group formed by this, the factor group, does this group provide any information about the abelian or non-abelian nature of the group? So the question answer is yes, it does provide us the information. How? If this factor group is cyclic, then our group is abelian. So this is the theorem and result that we have, and we'll be seeing its proof here. So here, in order to prove that, if we assume that G be some group and ZG be the center of the group such that its factor group is cyclic, this all has been assumed, we have to prove that G is abelian. So for proving that G is abelian, we need to show that each element in G commutes, right? So that means each element in G is also present in the center of G. Why? Because in the center we have all those elements which commute with all the other elements of the group, right? So if the group is itself equal to the center group, so that means we are taking the subgroup as equal to G, the trivial subgroup, then what all cofactors, what all members do we have for this cofactor group, right? This G Z of G. So what all members would be there, because if you are taking this to be G only, so we know G by G contain only the identity element within it, identity coset within it, right? So this factor group also would contain only the identity coset, and that is Z of G. Otherwise, what we do, we take some element A from G and we create cosets by defining it like this. For different A's, we have different such cosets, correct? And these cosets are basically the members of factor groups. Here, we are taking this element A as the identity, so such that we have ZG as the identity coset within it. If we prove this thing, we will be proving that ZG would be equal to G, and this would further prove that G is abelian. So this is our task. So here, because we are given that this factor group is cyclic, so that means it would be generated by some member within it. And what kind of factors are there in this group G, ZG, the factor group? It consists of all the cosets. So cosets, for cosets we need a coset representative which is taken from the group G, right? And then we take its coset by multiplying it with our given subgroup, which is ZG in this particular case. So in this case, the element would be of this kind, G into Z of G. So we say, because this is given to be cyclic, hence it is generated by GZG, right? This is one thing. Another thing, we can take some element A from this group G such that for this element, for this coset, now this is some random coset from this factor group, right? From this factor group, if we take some random element, it could be written as some power of the generator, which is GZG. That is what I have done. And if you take the ith power of your center, that would just be center, that is absorbed by the center, right? These are the properties of the center of the group. If you do not remember, please go back and look at the videos. Okay, so from here you obtain AZG is equal to GIZG. So here again, by the properties of the center, this would be absorbed by the center, so that we would have A is equal to GI of Z, where Z is some member from this center of G, correct? This is how we can represent it using the properties of center. Now, because G raised to power I and Z, they both belong to the centralizer of G. Centralizer of G contains all those elements which commute with G, right? This is the definition. Now Z, because it is the member of the center, would commute with every member of G. Hence, it would also commute with G in particular. And moreover, G raised to power I would definitely commute with G. There is no issue, right? So therefore, this G raised to power I is also a member of the centralizer of G. So if both of them are members of the centralizer of G, then A would also be a member of centralizer of G, right? Now, because we have selected this A to be some arbitrary member from G, what does it mean? It means that every element of G would commute with this G, right? If every member would commute with this G, by definition of the center, this G would be present as an element of the center of the group ZG. Hence, we can write GZG is equals to Z of G, correct? So this is nothing but exactly your center, right? And no other coset. This is the identity coset that we have. So the only element of this factor group is what? It is the center, which is the identity coset, and hence we have a result that G would be equal to ZG, and hence G would be abelian, right? This is what we wanted to prove here. Now, as a consequence of this result or theorem, we have further results. The first result here tells us that if G is cyclic, right? If G is cyclic and H is a subgroup of ZG, now we take H to be a subgroup of ZG, then G is also abelian in that case. So that means instead of taking G by Z of G, we now take a subgroup of this. Then the result also holds for that case. And we can also talk about the negation of this statement. What is the negation of this statement? The negation would be G is not abelian, one thing, and it is not cyclic, right? Another thing. So if we talk about the negation, it would go from here to here. So what does it mean? It becomes our second result. The result, when reversed, it is used most. And it says that if G is non-abelian, then this factor group is non-cyclic, right? This result we can quite frequently use in order to solve various problems. It is why that is so? Because using the Lagrange's theorem and using the above result, we have a non-abelian group, right? Because we are taking G to be non-abelian group, so it would be its order would be written as a product of primes, right? Any number could be written as product of primes. That is why where P and Q are primes. And if P and Q are primes, so therefore they must have a trivial center. Trivial center, right? You know what is that? If it has a trivial center, so it is not cyclic. So this factor group is not cyclic, right? Because if it has a trivial center, so ZG would not be equal to G, correct? ZG would not be equal to G. You can check this result. The result says if G is non-abelian, then this factor group is also not cyclic, correct? What about the third result here? Here the third result says if this factor group is cyclic, then it must be trivial, right? Factor group is cyclic, so it must be trivial. What does it mean? That means this factor group contains only the identity coset within it, correct? So I hope you understood this result well. Well, that is it for this video. Thank you for watching.